Right, so now that we have chosen our principal components that we are going to use, right, we have reduced our dimensions. Maybe we were dealing with 10,000. Now we are only dealing with 100. So we have our principal component or our z's. Our z we now have 100. We have to fit at least the second step is going to be fitting a linear regression, right? Fitting a regression, right? Using least squares. So let's do that. So in this video, we are going to just discuss quickly the principal components regression approach. So principal components regression, because what we were discussing previously was how to get the z's themselves, z1, z2, z3, etc. up to zm, which are our principal components, right? Which are our principal components. In this video now, we are going to, which are our principal components, or we're just going to call them our new variables, right? That's what we were discussing previously. So now that we have our new variables, let's use least squares on them, right? So we are going to fit a linear model. We're going to fit a linear model using least squares. And if you remember in the introduction video to dimension reduction methods, we said we're going to fit a model like this. It wasn't phi is for the z's, right? We said y is equal to theta naught plus theta 1 z1 plus theta 2 z2 all the way up to plus theta m zm, whatever m is going to be. Hopefully m is much less than the original p that we had. So often if we look at, like in the previous video when we talked about script plots and the variability and stuff like that, our hope is that a few of these principal components, a few of them are enough. That's our hope. We hope that just a few of them are enough to explain most of the variability in the data, as well as the relationship with the response. So those are two things that we are concerned about. We're concerned about the variability in the data, and then relationship with the response. So here what we are looking for in PCA, we want the z's to explain a large percentage of the variability in the data. If you have 94% of them, 94% being explained by z1 up to z5, compared to p equal to 10,000, we'll be like, yo, my goodness, let's just do PCA. Okay, that's one factor. We'll be like, yo, it's better for us to do PCA and just use five variables. The 5 new variables can explain 94% of the variability. Oh, we'll be so happy. The second part is the relationship with the response. We hope that these 5 that we are going to choose, that we have chosen because of variability, we hope that they are related to our y. Right? You are going to see in the next video, we're going to talk about partial least squares, because it then improves on this part here. With principal regression method, our assumption is these directions that we have chosen, because we chose these directions because of variability, right? And our assumption here, or hidden assumption, was that direction in which the original x1 up to xp vary the most, which is i.e. the directions that we chose, our z1, z2 up to zm, those directions, right? We hope that those directions are associated. We didn't state this, but that is the hidden assumption of PCA with y. That is the biggest assumption with PCA. We hope that these directions that we have chosen, these z1, z2, we chose them on the basis that these are the directions that the x's vary the most. And our hope is, if you vary the most in those directions, you're probably associated with y. That's what we are hoping for. But in reality, it is not always the case. That's where partial least squares comes in, but we'll see that in the next video. But so far, if that assumption holds, then with our PCA, we'll fit our least squares, right? We'll fit our least squares, and it will lead to better results than fitting the original P predictors, because most of the information in the data is being contained in M, which is much less than P, right? Much less than P. Most of the information in the data is in M variables, let's say 5 variables, compared to the 10,000 that we already had, which reduces our overfitting, because the other 10,000 they're probably just adding noise to our linear model, and we do not want them. We just want the very most important variables, right? So this one will fit much better than the original least squares if these two assumptions hold, right? The example results that you get is, let's plot our M, or the number of variables that we are using, our M, plot our M on the x-axis, and here we're going to plot our MSE, our MSE. What you probably see, what you see is, as more principal components, or as you increase your M, as more principal components are used, the bias is going to decrease. So your bias starts off there, and then it starts to decrease. It's going to decrease sharply like this. It's going to decrease sharply with the corners like that, right? The bias is going to decrease, and as you increase your M as well, your variance increases. Right? Your variance increases. As I say, this is the base case, best case like that. Cool. Your variance, it will increase. So what happens to your MSE? Your MSE is going to have its jagged corners, but even with these jagged corners, you can already tell that it is also U-shaped, like the normal shapes that we had when we did our least squares, right? The bias will decrease, but the variance will increase, resulting in this U shape that we are used to. So now let's say 0, 10, 20, 30, 40, 50, whatever it is, I do not know, right? Let's just say we had our P equal to 45. When our M is also equal to 45, PCR, our principal component regression, will equal it will equal least squares fit using all original predictors. I think you agree with this statement, all original predictors, right? All original predictors. So here it's a matter of choosing the right P, the right M. It's a matter of choosing the right M. And you can choose the right M using cross-validation. So you test when it comes to 10 M equal to 10, M equal to 15, M equal to 20, M equal to 30, M equal to 40, and then you see which one gives you the lowest MSC. So the other thing to emphasize is, if we have 45, let's just say this is when we have 40, the predictors that we had were 45. If we put M equal to 45, maybe we are somewhere here. So if we hadn't done any PCR, we only did least squares using the original predictors, and then we calculated our MSE. This was going to be our original MSE. I think you agree with that one. This was going to be our original MSE. So already you can tell that if we do a bit of PCR or PCA, principal component analysis, reduce our dimensions to maybe around 22, maybe around M equal to 22, we'll get an even lower MSE. So this MSE is now coming from PCR MSE. So this is the PCR MSE. So you can see, originally we had 45 predictors. If we do our PCR using M equal to 45, all of the predictors or whatever it is, we'll get this original MSE. But this graph shows us that you can actually lower your MSE even further if you reduce your dimensions. That is the power of dimension and dimension reduction. This PCR would do well. PCR would do well if the first few components, if the first few principal components are sufficient to capture most of the variation in the predictors, as well as the relationship. So without going to z equal to 45, if you can capture the variation or 94% of the variation when we are doing z equal to 15, we have 15 variables, and those 15 variables are related to the response, PCR will do very well. Bias would drop very sharply, way even sharper than we are doing here. It might drop even sharper, and the test MSE might be even like that, taking a shape like that, right? But what you have to be careful of is PCR. Even though we have m less than 15, you might be tempted to say, if we have PCR, we have like m equal to 15 instead of our p equal to 45. You might be tempted to think that PCR is feature selection method. It is not. PCR is not emphasize that a feature selection method. I think that makes sense, right? PCR is not a feature selection method. Why? Because remember, our z is a linear combination of all our x's. Every z is a linear combination of all our x's. So we really haven't done any what do you call this? We haven't done any dimension, any feature selection here. Hidden inside our z is all our original features. We've just reduced the dimension that we're working with, So that is principal component regression. And of course, like most machine learning algorithms, it is recommended that you first standardize standardize the features before generating those principal components. So you know what I mean? Before we generate all these z's it's good practice to just standardize our x's. Standardize your x's, subtract them, the what do you call this? Subtract the mean, and then you divide by the, if you want, you can divide by the standard deviation or whatever it is. Just standardize them before you so that they are an element of, like, if they are numerical, they're like in between 0 and 1, so that the scales do not affect. Because imagine x1 is income in thousands, and then xp is population of countries in millions. That's just too nasty. Nah, standardize xp, make sure it's between 0 and 1. Standardize x1, make sure it's between 0 and 1. That makes it much easier. And then you calculate your z1 to zm, and after you calculate your z1 to zm using the principal component analysis that we did, finding those directions with maximum variability, using a script plot or whatever to get the ones that have that will give you the variability that you want, that are covering the variability that you want. And after that, you have your set of z's, and your set of z's use least squares to fit the linear model, and after that, just check which m you want using cross validation, and you're done. So that is principal component regression. And like I emphasized, principal component regression has one problem. We are not sure whether the z's that we have chosen, because as you have seen here, as you saw, when we were creating the z's, right? We didn't even think about y at all. We didn't even care about y. We actually ignored y. Y was somewhere there shouting like, guys, do not ignore me, but we're like, we do not care. All we wanted to chase the variability in our data. That's all we cared about. Like, our data, where's the highest, which direction is the highest variability, give it a z. That's what we cared about, right? And then, so actually we are banking on this assumption that the direction in which these original data vary the most are associated with y. But this assumption sometimes fails. It sometimes fails, which means we are actually going to regress y we are going to regress some z's onto y where they don't have any relationship. They don't have any relationship, and that is where partial least squares comes in. This is because when we are choosing these principal components, it is unsupervised. It is unsupervised. It's an unsupervised method. Unsupervised, which means y is not checking up on these guys if you are doing the right thing. Y is not even involved at all. So it's unsupervised. But partial least squares is supervised by y, and that improves on our relationship to make sure that the directions that we actually get out of that are going to be related with y. Let's see that in the next video.